Hello everyone, this is RanadhirBharadwaj, EE275 Computer Architecture. I would like to introduce my project. I would like to present my project, a 5-stage EOS2 processor for EE275 Advanced Computer Architecture. And I would like to uh, thanks Professor Chang Chu for giving me this wonderful opportunity of San Jose State University. Let's go into the project in detail. The main agenda of the project is to design an EOS2 processor with a given test vector and find the following. The following consists of the sum of array, dot product, and the factorial. The overview, going into the overview, it consists of introduction, background, design of hardware implementation, design environment and verification, test bench, analysis, simulation results, future work, biography, and references. Going to the introduction of the NEOS2 processor in detail, the NEOS2 processor is a soft-core RISC architecture, reduced instruction set computer architecture, which means it can be implemented on any FPGA platform of Stratix or Cyclone family. It's a 32-bit architecture, so all the included entities are 32-bit wide. It supports implementation of 256 custom instructions. The MIPS architecture is a reduced instruction set computer architecture. In this, the architecture doesn't perform individual instructions to perform complex and logic intensive tasks. MIPS believes that by only implementing a small code that is only a few dozen instructions instead of several hundred of most of common instructions, one can simplify the design and speed up the majority of the common instructions. And another point is the data accesses to the memory locations and the IO interfaces are performed by the means of load and store instructions, which causes data to be transferred between the memory and general purpose registers. And another point is the off-chip memory devices such as SRAM, SDRAM, and the flash RAM chips are accessed by instantiating the appropriate interfaces. The NEOS2 processor. The NEOS2 processor consisting of different kinds of addressing modes. We'll go through them in briefly. Its addressing modes are mostly the immediate mode, register mode, displacement mode, register indirect mode, and the absolute mode. The instruction formats, three kinds of instruction formats: O format, I format, and J format. Instruction set architecture nears to processor or format instruction set architecture, and what's up code, and what are the bit fields consist of. It consists of 32, as it is a 32-bit architecture. You can see the OR format consists of 31 to 27 MSB of A, 26 to 22 of B, 21 to 17 of C, and 16 to 6 of OPX, and 5 down to 0 is an opcode. I format of ISA. You can see that 31 down to 27A, 26 to 22B, 21 to 6 immediate, and 5 down to 0. It's an opcode, and below the I format you can find add immediate or ORI, load word, store word, BLT, and the branch instructions, everything as well. Implementation of 5-stage pipeline. The 5-stage NEOS2 processor. The main principle of the 5-stage pipeline is breaking the instruction across multiple clock cycles, 5 in this case. Design a separate stage for the execution performed during each clock cycle, adding a pipeline register to isolate signals between the stages. The NEOS2 processor consists of test bench, processor module, fetch module, decode module, execute module, memory access module, write back module as well. Going into the block diagram of the NEOS2 processor, it consists of a test bench and the top level module. The top level module, as I discussed, it consists of fetch module, stall detection module, memory access module, write back module, execute module, decode module. The top module interfacing with the test bench and the sub modules of the design that are interconnected to execute NEOS2 instructions. Data and instruction memory is a part of design. Every instruction is fetched for execution from the instruction memory to perform its respective operation. Going into the architecture of the NEOS2 processor, the architectural diagram of NEOS2 processor, it consists of 5 stages as we discussed: the fetch stage, decode stage, execute stage, memory access stage, and the write back stage. You can see the PC, the program counter, the adder, the multiplexer, the instruction fetch, instruction memory, the IR register, the registers, the design extended, add, and everything else, the marks data memory going. It's how the instructions are data are fetched, and the it's overall architecture of NEOS2 processor. This is a sample program showing you the dot product of two vectors, programs for the dot product or HIR to RO, and if you want you can pause the video and go through the dot product. It consists of three types of formats: I type, R type, and I type, etc. You can go through that. The program is running in a loop until there is a stop. Going to the execution time versus the speed up time. The speed up is defined as the execution time of a sequential program divided by the execution time of a parallel program that computes the same results. In particular, let's say speed up is equal to Ts by Tp, where Ts is a sequential time and Dp is a parallel time. Running on preprocess, speed up is often plotted on y-axis and the number of processes on the x-axis. You can go check the figure, check the graph. You can see on x-axis the process and the y-axis and the speed of time. If there is an ideal speed, it is of 45 degrees, but according to the Amdahl's law, there is an inclination towards the process. Yeah, the figure constructs the figure. It shows that a typical speed up graph showing performance for two programs. The speed up graph shows a characteristics typical of many parallel programs, namely that the speed up curves level as we increase the number of processes. This feature is a result of keeping the problem size constant while increasing the number of processes, which causes the amount of work per processor to increase with less work per processor. Costs such as overhead or sequential computation, as Amdahl's predicted, become more significant, causing the total execution not to scale well. These are the simulation results showing the 5 stages: instruction fetch stage, instruction decode stage, execute state, and the memory stage. You can go through that in detail. If you are going to check the report, you can know in detail. Summarizing the simulation results, we are now going to look at the sum of arrays program. Here you can see the test vector of sum of arrays is obviously my FZSUID. It's 0998575, which is stored in R3, 0 which is of 2 cycles, 9 which is of 2 cycles, 8, 5, 7, 5, 5, and 5 is of 2 much length. It's because of 2 cycles, and the 30 which is marked in the yellow, you can see SJSU ID 0s9985755 implies 0 plus 9 plus 9 plus 8 plus 5 plus 7 plus 5 plus 5 equals 48. 48 converted to hexadecimal 30, which is obviously stored in R1. You can see that it is 30 in hexadecimal. It is a sum of arrays. So going to the dot product, you can see the test vector for the sum of arrays is again my SJSU ID at 099855755, which is stored in R6 register. Coming to the dot product, the dot product calculations are shown in the blue box. Register R5 equal to 00AA, 00A2, 0144, 01Z4, 01FB, 025 at 0280. SJSU ID initial digit is 0, so dot product is 0. The second digit is 9, which implies that 9 into 2 into 9 equal to 1 equals 162 in hexadecimal is 0082. So in this way, all other digits are calculated and perform the operation, and the yellow ones are results. You can check the cross-verify the results. Coming to the factorial here we are trying to perform is the factorial of 3, which is 3 into 2 into 1 equals 6, which is obviously stored in the register R2, and the test vector which is stored in the R6. This 5-stage needs to processor features 32 into 32 cross 512 locations of instruction memory, 32 cross 32 internal registers, 32 cross 1024 data memory locations incorporate data hazard detections unit, which avoids raw by read after write by using stall conditions. It takes 266 cycles to complete entire operation. ALU control is incorporated within main control unit. The conclusion: the 5-stage needs to processor is designed and verified using my own test bench. Each and every block in the processor is verified by different test benches and observed the waveform. The final result, that is store operation in which 800 memory location is loaded, is observed by using display statement in the memory block. And the future work, there is a lot of future work to do. The future scope of the design are: the main thing is the data forwarding, and the bypassing unit has to be implemented in this design, and design has to be synthesized and to achieve the frequency of 200 megahertz. Power optimization techniques as well, like clock gating and other methods, can be implemented to increase the efficiency of the design. The ALU control signal is 3-bit wide, so the ALU can perform 8 operations. Currently only 4 operations are implemented, so 4 more instructions can be implemented. Branch unit can be moved to a previous stage to reduce Stalls in the branching. The main instruction currently has 5 locations. As the bus width is 32-bit wide, 232 locations can be addressed, so instruction memory can be increased to accommodate lengthier programs. The data memory currently has 1024 locations. As the bus width is 32-bit wide, 232 locations can be addressed, so data memory can be increased to accommodate more data. Additional cache memory and data forwarding unit can be implemented. Going to the references, these are all the references which I have gone through to make this project. Mm. This is my biography. I'm RanadhirBharadwaj, pursuing Masters in Electrical Engineering, VLSI, San Jose State University, graduating in December 2016, completed my undergrad, so and so. And I have a 3 years of work experience with a Hyundai Motors Research and Development as a graduate engineer trainee, and later promoted as a research test engineer. Worked for 3 years on MATLAB device drivers, Linux device drivers development for specific microcontrollers. And the major projects which I did are simulation and verification of immobilizer, implementation of design specification, control logic simulation of immobilizer ECU software, and W architecture for Indian market. That's it from my side. Thank you for your attention. If you have any queries, please feel free to reach me at my email ID. My first name Ranadhir.Bharadwaj, the last name at gmail.com, or you can call me on 669 226 8158. Thank you.